So I want to start with some gentle introduction. So here I drew examples of tensor networks. What you can see at the moment is some drawing. It doesn't have to make a lot of sense to you, but during the week we'll understand better and better what these drawings mean. And just so that you get started or used to these names, I will be talking specifically about concrete types of tensor networks. This one here, in a one-dimensional array, it's a matrix product state, or MPS. That's how it's referred to in the literature, MPS. There is also another one which we'll also study, which is called multi-scale entanglement renormalization ansatz, or MERA. And this one spreads not just in one dimension, but in an extra dimension. And also, we'll be seeing projected entangled pair states, which look like that. Okay, so we'll make sense of this during this week, what this drawing is. So we want to start. Oh, by the way, I sent you an email with a PDF, so you should have some figures so that you don't need to draw them. Very good. So let's start with first, why tensor networks? Why should we care about, and where are they coming from? So last week we saw that if we look at ground state, entanglement ground state of local H, if we look at entanglement, we saw this area law or some pattern. There was an area law, some characteristic scaling that made it these states look different from generic states. And what we're going to see this week is that this suggests that a tensor network description of these states might be possible. Okay, this property, this area law, suggests that tensor network description might be possible. And what we'll see is that in order to characterize the ground state of a local Hamiltonian, we'll be using a set of tensors, say, of this form. And what we'll see is that this description in terms of tensors is somewhat local, okay, in real space. And most importantly, efficient. It will be order n. We will be able to describe these ground states with computational cost, which scales linearly in the system size, as opposed to exponential, which would be a random state, a generic state of the Hilbert space. Okay, so that's what we will see, and then we have to write grams and make things look shiny. So let me do this. Let me describe tensor networks as I would do if I had to write a gram. So I would say the following: they are a natural language to describe for many-body phenomena. So on the one hand, I'll argue that it's a natural formalism to be using there. And on the other hand, I'll mention that this is the basis for numerical approaches. So I want to make this distinction. I want to make clear that tensor networks are not just something you do with numerics, but it's also a natural way of talking about many-body states. And so to give you examples of these which do not require numerics, tensor networks in recent years have been used to classify possible phases of quantum matter. So classify quantum phases of matter. So-called symmetry-protected topological order. This is just a pointer. So I'm not trying to explain to you what these phases are, just that if you see such SPT phases around, then you make a connection to tensor networks. It's been used to reformulate real space RG, the renormalization group. Okay, and that will be connected the same way that actually the classification of quantum phases of matter in one dimension are connected to matrix product state, using this as a natural way of describing ground states. The renormalization group in real space has been reformulated using ideas from this other tensor network called multiscale entanglement renormalization, ANZEDS or MERA. And in particular, when I hear reformulate, maybe I'm just rewriting things, but actually, no, this way of viewing the renormalization group has led to important benefits. For instance, these approaches, the same approach, the same renormalization group ideas, apply both to ground states of quantum systems or to partition functions, and it has led to a new notion of RG, which is this branching. So there are a number of advantages, and in particular, it led to this idea of branching renormalization group, okay, where as you constrain the system, your system breaks into pieces. Very good. Or another example where we are not using numerics, but just trying to understand new ideas. These tensor networks are currently of interest because they bring, in the context of holography, so we obtain new insights into holography. Through toy models. And these toy models concern both geometry or space-time, emergence of space-time geometry from entanglement, as well as error correction. Okay, so there are currently several ideas in holography that are based on tensor networks and are being explored. And another development, which is actually not completed yet, its current research, is extensions from Lattice. So in this course, we've been talking about the lattice all the time, and we'll use tensor networks to describe ground states on the lattice, but we'll see, or let me tell you that there are currently significant effort in bringing this also directly to the continuum. And this would be a reformulation or better understanding of, so reformulate quantum field theory. Okay, so these are big words, but it's actually happening. There are attempts to do these things, and that has nothing to do with numerics. However, tensor networks were originally introduced as basis for numerical approaches, and so the idea here is you have a Hamiltonian, and you want to find the ground state, and so these approaches are going to be variational. Okay, we make the assumption that our wave function, in some sense, can be written in this way. That's a restriction on the type of wave functions we can have. And this started being successful in condensed matter. And now I'm going to stop writing things and generate. So tensor networks have been used in condensed matter in the context of quantum critical systems, and topological order, frustrated magnets, interacting fermions. And then, let me go to the list. And they are, but this started in condensed matter, but it spread beyond condensed matter, and they are currently used also in quantum chemistry, statistical mechanics, quantum error correction, image compression, machine learning, and quantum gravity. Okay, so it really has had influence in a number of fields, but the most important point is that this is still under development. We don't know how far we can get. So there is a lot of research to be done there. Very good. So that would be the end of the grant proposal. And now let's go back to our course. So in this course, what have you been provided with So this course, okay, we've seen basics or basic computational skills. And that would be, we've been using Julia, so you've learned a little bit about the language, and also algorithms, concrete algorithms, say exact diagonalization or power law, power method, or Langtos. So basic algorithms that you can now use to diagonalize a Hamiltonian. And in this course, we will also, well, we'll have theory both of entanglement last week and tensor networks this week, okay? But implementing these algorithms goes, so these tensor network algorithms, seeing how to numerically use these tensor networks, that goes beyond the scope of this course for many reasons. Time limitation, also it will be too specialized. But I want you to know that you've been provided with everything you need to just jump into that. If you are interested in learning tensor network algorithms, you already have the basic computational skills that you need, okay? And also after this course, you should be able to understand all the ideas that are underlying these algorithms, so you should be able to do that. And what I'm going to do is I've asked Eric Schnetta to make a presentation on Julia, possibly next week, so he will give you a better picture of what Julia is about. Now that you have some initial experience with it, he'll give you complementary information about it. And also possibly, if anybody is interested in learning more about the algorithms, as I said, you have all the basic material ready, so we can talk more. Very good. So let's start with the lecture. The first thing I have to do is to introduce some diagrammatic notation. Which we kind of have started to see last week. Okay, so I'll be drawing lots of things. And so this will be a way of denoting tensors. If you see a circle with one leg, then this corresponds to some vector. Okay, so the leg corresponds to the index. There is one leg, one index, therefore it's a vector. If you see a circle with two legs, could be a circle, a square, anything, then this would correspond to a matrix, okay? And so on. 3 legs. Etc. Okay, so we want to understand what these drawings mean. And the first thing I say, every time you see a circle with a number of legs, that's a tensor. In this case, this tensor has 3 legs, so 3 indices. And this one has 4 indices, and so on. Okay? So question for you, if you see a circle, what is that? Sorry? Complex number, scalar? Okay, very good. That was easy, huh? So the second part of this notation is that what we call tensor manipulations. And again, it's very simple. If you see, so we're going to sometimes write equations like this. Okay? And when you see this, what you have to think is, okay, that's a vector, right? Let me write a vector here. That's also a vector because it's a circle with a leg, so let me call it x. And this is a matrix. It has 2 legs. Okay? So this would be the notation that we use to denote multiplication of a vector times a matrix. The rule here is that if you see an index that is shared by 2 tensors, there is a sum over that index. Okay? That's what we would have here in components. This is I, M, I, J, X, J, sum over J. Okay? So the sum is here. This would be J. All right? Very good. So similarly, if you see this equal to that, what is this saying? What is this? Sorry?
Matrix multiplication.
So the multiplication of two matrices, which gives us a matrix. Okay, very good. So if you see, I don't know, this one says a number that is the product of a vector times a matrix times a vector. This could be if we are looking at the expectation value of an operator. Okay, so this could be psi, this could be the operator, and so on. Okay, very good. I think everything is clear. So now imagine that we have a state on n qubits. Then we can represent it with a tensor with n legs. That's right. Well, I mean, we've seen this, right? That's easy to follow. So what I want to ask is, how do we represent the norm of this state? Okay, the norm of this state is going to be something like that. Okay, where we contract all the indices together. Okay, final question, and then we can move on. What is this? This is what? It's a trace of the product of four matrices. Okay, very good. So we'll need all this. And now we can move to the definition of a tensor network. So we consider vector space of n particles or n sites on a lattice, and we're going to assume that the dimension of each site is d, and then the vector space is the tensor product n copies of CD. And we're going to consider state psi of this Hilbert space, and in general, you know that we can expand this in a product basis. These are the coefficients, and then we have the vectors in the product basis. Good. And as I just mentioned, we're going to represent this, or we could represent this as a single tensor with n indices. Now, a tensor network is going to be a re-expression of this state using some more complicated looking structure. And I'm just going to draw a concrete tensor network for the sake of completeness. But so the idea is that we'll have I1, I2, In. The idea is that we will have in this tensor network, this will be just a collection of tensors. Okay, each circle is a tensor, and the indices, or most of the indices, are contracted. Okay, but we will also have a number of indices which are open. Okay, so actually, if here we have n open indices, on the others here we will also have n open indices. I'm going to refer to those as physical indices. Okay, I'm going to call these the open indices, physical. Okay, and we'll have n of them. And I'm going to refer to the indices which are contracted with each other as Born indices. Okay, and then the first thing I want to do is I want to compare how many coefficients we have on this side, which you already know the answer. It's d to the n coefficients. And I want to count how many indices we have, coefficients we have on this side. Okay? And to do that, I'll have to say that there is a limitation here, which is that we will use order n tensors. So on this side, we'll just put together order n tensors, a number of tensors which grows proportional to the size of the Hilbert, to the number of sides on our lattice. Okay? And I'm going to assume, so this bond index in general will run, each bond index, say alpha, runs from 1 to some value chi. The physical index, say I, goes from 1 to d. Okay? I'm going to assume that tensor size of tensors is independent of n. So for instance, a tensor in here, say this tensor here, looks like that, has 3 bond indices. Each one runs from 1 to chi. So the size of this tensor, how many coefficients it has, is just the product of the sizes of the indices. So this size is chi to the 3. The important thing here is that this is independent of the system size. Okay? It does not depend on n. It's chi could be 1,000. Then this would be 10 to the 9 coefficients. That's fine. It does not depend on n. So if we assume that, then what we have here is that we have that the total number of coefficients is whatever number, fixed number of coefficients its tensor has, times the number of tensors, which is order n. So we have order n coefficients. Okay? That's how we're going to work. We're going to put together a number of tensors. The number of tensors is going to be proportional to n. And if these tensors, the size of the tensors is fixed, then automatically we have a representation in terms of only order n coefficients. Question?
Yeah, the tensors in the lowest row, they have one index that runs from 1 to n.
Yes.
Now, if we increase n, would we need more coefficients there?
Okay, so right. I took a particular tensor from here, and I said, let's assume that it has some given size, chi3. If we look at, say, these tensors here, they will have another size. Okay, it has more legs. But what I want to take from this example is that each tensor has some finite number of coefficients, which is independent of n.
But
okay?
We can't make the number of coefficients in the tensor in the lower row independent of n, can we? Because one of the indices runs over n values.
No. The indices, these indices, the lower indices run from 1 to small d.
D,
right? Which is the dimension of the local Hilbert space. If this was spin 1/2 particles, it would be 2 values, up and down, right? So these tensors have 3 bond indices and a physical index. And I'm also going to assume that the bond indices take only chi values, where chi is independent of the system size. Okay? All right, very good. Yes?
Can I ask a question? When we describe the any ket psi, the corresponding, the corresponding tensor network should have always that kind of structure, the square lattice form, or that is just a schematic?
The form here will be replaced with, say, those forms then, or something else. I was just giving you an example where it's clear that in this example that the number of tensors is proportional to n. Actually, there are 2 times n tensors here. Okay, but that's a concrete example. There will be other examples that we can consider. Did I answer your question? Okay, so is that possible in general? Can this generically be true? That is not possible, right? Here we have e to the n coefficients, so exponential in n. Here we have a linear number. Okay. So what that means is that this will only be true for a subset of states in the Hilbert space. Okay. We throw random coefficients here, we will probably not have this description. Only some type of states will have such decomposition. Very good. Yes, and I want to emphasize what it means to have exponential growth versus linear growth. So imagine that we have n spins here, or n sides, and we add 1, okay? How does this affect the number of coefficients we have to store in our computer? Well, if we were, in this case, we have to multiply times the number of coefficients, okay? So if you were already working at full capacity with your computer, if you want to add an extra side, you have to buy d-1 new computers, okay? That's what it really means. And you cannot do this many times because it's really growing exponentially. Sorry, the number of computers you would have to buy would grow exponentially, and that could be a problem. In this case, what happens if you add an extra side? It means that you have to add an extra tensor or 2 or whatever. So you have to, when you go from n to n plus 1, the number of coefficients, you have to add some number, okay, some constant. Okay? Order 1 could be 1,000, order 1,000, that's fine. Okay? You just, the number of computers you have to buy is proportional to the system size. That's good. All right, so examples of this. Examples of tensor networks. Let me start with very, very simple example. Today we'll treat only 2 examples, and then the rest of the week we'll look at the serious ones. But today we will really build intuition of what it is that we're after when we try to design a tensor network. And then we'll see how those examples, those concrete tensor networks fulfill these requirements. Okay, so example number 1, it's embarrassing. But still, we can learn a lot from it. It's going to be a product state. Okay, so imagine that our wave function of n spins, or n sides, is the product of individual states for each side or spin. Or in components, this means that psi I1, I2, In is equal to phi 1, I1, phi 2, I2, phi n, In. Or if we use our diagrammatic notation, we have psi here, and here what we realize is that we need to specify a vector, phi 1, for each side in the lattice. That's what this means. Okay? So that's there is a product of such things. That's our notation. So this corresponds to a tensor network where the bond dimension connecting different tensors is 1. There is no connection between tensors. Okay? That's the same as saying that there is an index which only takes a value, so we can ignore it. Okay? But this example helps us because it tells us what the role of these indices that we have connecting the tensors is. Okay? This state we'll see that has no correlations there are no correlations between sides. So next time you see as part of a tensor network an index connecting to tensors, you already know, okay, intuitively what this is doing is allowing entanglement and correlations between the parts of the system. If we had no such index connecting the two tensors, there would be no correlations or entanglement across. Okay, so, and the second example I want to deal with, it's going to be a quantum circuit of finite depth this is we're going to consider a state, a wave function, such that we can decompose this tensor, or we can rewrite it as a quantum circuit. Now, if you've been studying a lot of quantum computation, you know what I mean by this, and if you haven't, it's no problem, because it's easy to describe what this is doing. So we're going to consider this state that we're encoding here as the result of doing the following. We start with the product state, okay? Product state 0, 0, 0. And we apply this quantum circuit U to it. And that is what our state ends up being. Okay? It's the result of applying sequentially all these gates, two side gates, to initially a product state. Okay? So I'm not proposing that we go to a lab and prepare this state by applying a quantum circuit to it. I'm proposing that we think of this as our variational state, as our tensor network. So if you look at this, what we're saying is this looks like a tensor network, right? If you take an index and you fix it to state 0, it's as if the index is gone. So this thing here looks like a tensor network. Instead of circles, I'm using squares. I think you can cope with that. And then what I'm saying by finite depth is that the number of gates here, the number of rows of gates, is some finite number t. Okay? T rows of gates. Okay. So what I'm saying is that we can specify a state of n sites by specifying the content of these gates. These gates are, what's a gate? This gate is some unitary map between two copies of the Hilbert space. So this goes from CD tensor product into CD two copies, right? So it would be d square times d square matrix with some unitary constraints such that, which mean that if this is small u, then if you conjugate it, multiplied by its conjugate, then you get the identity. Okay, this is what it means for u daga equal to u daga u equal to the identity. Okay, so what I propose is that we think about the type of states that can be created in this way. Okay, so okay, very good. So now I could come up with many other proposals, maybe those, and the question is, what's important in a tensor network? Right? You could come up with your own proposal for a tensor network, and what we need to understand in this class is what tells a good tensor network, a useful tensor network, from a useless one. And so I want to discuss three conditions, three properties that we want to demand to a tensor network before we take it seriously. That's 6.4. What makes a tensor network useful? And so I'm going to be referring to these three conditions for the whole week. The first one is going to be efficient specification. maybe we want to see that psi is determined or specified by, for instance, by order n parameters, coefficients, or maybe order n square, okay, but not exponential in n. Okay, that's the first thing we want. We want an efficient description. But this is not enough when it comes to computational aspects. We also want to be able to efficiently extract information. So I'm going to call this efficient manipulation. So for instance, I want to be able to, given that wave function, I want to be able to compute expectation values of local observables. So computation of expectation values. Of local operators, say O is sigma Z acting on site 24, right? So there is no point in having an efficient representation of a state if I cannot know the properties of the state, if I cannot know how much the energy is or the magnetization is or anything. Okay? Efficient manipulation would be, for instance, computation of expectation values, or given a Hamiltonian, how to use these answers to find the ground state, okay, optimization. How do I optimize this tensor network as a variational ansatz? How do I determine, how do I fix the parameters in these tensors so that the tensor network approximates the ground state of my favorite Hamiltonian? Good. These are computational aspects that are important. But in addition, in the end, we also need to demand perhaps the even more important property, which is that the tensor network should offer an accurate approximation to some state of interest. So maybe a ground state. Here we'll be interested in ground states, or to ground states of local Hamiltonians. Okay? And what that exactly means, it depends on the context, but imagine we have the exact ground state, and then we have our approximation through a tensor network. What we're saying maybe is that we want this overlap to be close to 1. That would be a fidelity. But maybe that's too demanding, and maybe it's enough that the expectation value of local operators be approximated. Okay. But in the end, what we're saying is we would like to learn about physics, which are represented by the exact wave function, and we're trying to find a way of learning about that. So if our tensor network gives us already good approximations to the physics that we want to extract, then that's fine. Okay?
Can the tensor network provide good approximation for the non-local operators, like Wilson loop?
It might. So if you are interested in a problem where Wilson loops are the relevant operators, the relevant observables, you will use. It only makes sense to use a tensor network that is actually giving you that. Yes. Very good. And there are many things that we could look at, but instead of looking at expectation values, what we will do here is we will ask, we'll focus on analyzing structural properties of the tensor network. So we'll be looking at, we'll take a tensor network and we'll ask, what type of correlations can it represent? Okay, can it represent power law correlations or exponentially decaying correlations? And also we'll look at the entanglement entropy. Okay, we'll be looking at the scaling of entanglement entropy. So the idea here is that we cannot look at all, we cannot study this unless we decide what problem we're interested in, but we can, this criterion looks problem dependent, but what we are interested in this class is to understand whether at least a variational ansatz, a tensor network, a concrete tensor network, is compatible with, say, power law decay of correlations and a logarithmic scaling of the entanglement entropy. These are properties that we've studied last week. We've seen that those properties appear in ground states, and so we'll use that as a guide to decide whether this tensor network, this concrete tensor network, could potentially be a good approximation to those ground states. Okay? It doesn't guarantee anything, but at least we know that things seem to be right. Very good. So what I want to do then is, tomorrow we'll look at these properties for a matrix product state, the day after possibly for the meta. But today I want to look at these properties, A, B, and C, for a product state, right? For the two trivial examples, or the two examples that we discussed before. Very good. So let's start with the product state.
About how to construct the state using the tensor network. Like, can you give a more concrete example? Like, if the state is given, then how do we construct the corresponding tensor network?
We are not ready to do that. We will only see this in some, for instance, tomorrow with a matrix product state. At the end of the lecture, I'll explain how to do that. But do you agree that if I give you the tensor network, then you can represent the state? Do you agree that the tensor network gives you all the coefficients that you need? If I give you something like that, it has 3 open indices, right? So every time I fix the values of these indices, it gives me some complex numbers, right? Because once I fix the value of the indices, those indices disappear. I get this. There are no open indices. That's just the trace of the product of 3 matrices, right? So that's a number, some complex number. And I can do this for any choice of these indices, right? So you could start with this index being 1, 1, 1. I get a complex number. 1, 1, 2. I get another complex number. I do this for all possible values of the indices, in this case d to the 3. And I get d to the 3 complex numbers. This is precisely what we mean by this, right? So my wave function is equal to, and then sum over I1, I2, I3, and then psi I1, I2, I3 in this local basis. And I just told you how from the tensor network, how to extract all these coefficients. So that completely specifies the wave function. Okay? I think that's a very good question. So I hope it's clear that if I draw something like that, I mean if I draw something like this, you have to think, okay, there are d to the 3 coefficients encoded here. I may use less than d to the 3 coefficients to encode them, but I could extract all of them if I wanted to. Okay? And once I have them, I put them here, and that's my wave function. Yeah. Okay. So let's go back to our simple example, example 1. I want us to discuss the 3 points up there. A, efficient specification. Well, that one is simple, right? We said, let me write psi again, phi1, phi2, phi n. How many parameters do we need to specify this state? So remember phi1, there will be some local basis I1, and we can specify it by using phi1, I1, I1 goes from 1 to D. So it takes D coefficients, D complex coefficients. We're just specifying the state of one spin, okay, of dimension D. So we need to do this for phi2, phi n, all right? There are n of those. So how many coefficients do we need? So it's n times d, which for us it's just order n, okay? So, you can consider many large such product states. The cost is only linear in n. Very good. So that was A, efficient specification, tick. Okay. B, can we efficiently extract information from it? Okay, can we efficiently manipulate it? And to study that, we can ask questions like, can we compute the norm of the state? Or can we, as we said before, can we compute the expectation value of some, say, single site for simplicity, some operator acting on the third site? Okay, I want to answer these questions. Now, we can see that if the state has this form, then this product, scalar product, becomes of the form. It's the product of individual pieces. Okay. If you want to make it look tensor network like, we're just multiplying this phi1 star, and so on. Right? We have that our product has broken into the product of individual scalar products, n of them. Okay. So this we can do again with order n cost, right? You know how to multiply this with cost which is proportional to d, and you have to do this n times and then multiply things together. So that's cost order n. Okay. So tick. We can we can compute the scalar product. Let's look at this one now. What's this one? Well, let me draw it in that way. So what we're saying is that now we have an insertion here corresponding to an operator on side 3. Okay. In the end, this is again this expression, just that for m equal to 3, we have to make an insertion. Okay. But that's again no problem because this is a matrix multiplication or vector matrix vector, but this is dimension d. So you can do this with cos d, which is the same leading order as multiplying any of those. So again, order n. So we're good. We can do anything we want with product state. Okay. So now finally, I can say yes. Tick. Very good. So now the tricky question, though, C. Is it a good approximation to anything? So good. Is it useful? Okay. So to answer this question, let's look at correlations, how correlations scale with distance, and also at entanglement, how the entanglement entropy scales when we consider a region of size L. So correlations. Well, what we want to do is we want to compute something like this. We put an operator on side L. We put another operator on side M. Okay. But what does it look like? This looks like phi. This is the cat. I'm drawing it on top. Maybe I'll do it slowly. Now I'm going to side L. I'm going to side M, and I'm putting an operator. Okay, that's the product. This thing is a tensor network for just this part. Okay, I'm multiplying the vector, the psi, which is on top, times an operator on side L, which is here, it's a matrix, times an operator on side M. And now I want to take the scalar product of that with the state. So I get this. Now remember, I'm not trying to find out whether I can compute this efficiently. It has already been established. What I want to point out now is that after we've normalized all these states, so individual states, this gives you a 1, okay? This gives you a 1. This gives you a 1. I don't know what this gives you, but I'm just going to leave it like that. And I notice that that would be exactly the result if I was computing psi O of L psi. Okay? This guy here would be put an insertion on side M, right? This expectation value of a single operator would be of this form, and then we would argue again that this goes away because the state is normalized, right? So we have this expectation value here and times this expectation value there. Okay? So we see that the 2-point correlator that we want is the same as this product of two terms, but that just means that psi of OL OM psi minus that minus the individual expectation values that this is 0. Okay? But that's the connected correlator. So what we are saying is that there are no correlations. That this wave function has no, the connected correlators are trivial, are 0. Okay? So it's not that we have either exponential decay or a power law. No, 0. All right? Or to be generous here, we could say delta L M. On site, there are this correlator is non-trivial, but there are no correlations between different sites. Okay? So that's kind of disappointing because ground states do have correlations. What about, so this was correlations. And now what about entanglement entropy? And here what we can say is that, well, let's take, let's compute row, say 1, 2, which means we're going to take part A of the system to be just made of sides, the first two sides. So we consider tracing out sides 3, 4, n, okay, as an example. And if you do that, you notice that, well, actually, what you are tracing out is here. And this will give you a number, which is by normalization 1. And you're left with a projector onto a pure state. Okay? So that means that the reduced density matrix is a pure state. It means that it has a vector of probabilities of eigenvalues, which is 1, 0, 0, 0. Right? And the entropy for that is 0. Okay? So entropy as a function of the size of the region, say A here had 2 sides, but now we can do the same for any number of sides. Okay? So as a function of L is 0. So we're seeing no correlations, no entanglement. Okay? So yeah, it's very cheap computationally, but it's giving you something that, so it's a subset of states that do not look very much like ground states of interacting systems. Okay. And nevertheless, actually, these product states are very useful, okay, to get the first idea of what's happening in a system, at least for systems with symmetry breaking order. And to understand why, let's consider, say, our favorite quantum Ising model. So Ising we have, say, the Hamiltonian sigma x plus h sigma z, as we did during the first week with the minus sign here. That means sum over nearest neighbors, blah, blah, blah. And here what we can plot is the magnetization, which will be expectation value of sigma x. Okay, that's the magnetization as a function of the magnetic field. A magnetic field equal to 1. Remember, we had the phase transition. And what you see is that on the ground state, it looks like this. The magnetization comes from a finite value to 0 at the critical point. Okay, and the important observation is this: that in the limit of large h, the ground state is an eigenstate of sigma z. So it's on each side. So it looks like this. Okay. It's a product state in the limit of large h. For large magnetic field, the ground state is a product state. For 0, in the limit of 0 magnetic field, when this term dominates, you have two different ground states, the symmetry breaking ground states. One is plus, 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 and the other one is minus, 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 where these plus or minus are defined as 0, plus, minus 1. Okay? So this you probably already knew, and I'm just reminding you that when we have a symmetry breaking phase, the ground states deep in the phase, okay, deep in the large magnetic field phase or in the no magnetic field phase, disordered or symmetry breaking, the ground states are product states. Okay? So if we make the ansatz that we have a product state throughout the phase diagram, we'll get it right here. You'll get it right here. You'll get it wrong in between. But actually, you'll see that you can get very close to the critical point and still get, roughly speaking, the right type of, for instance, your approximation of the ground state by a product state here will be incorrect, but it will be symmetric. Okay? And your approximation to the ground state on this other side might be incorrect, but it will be symmetry breaking. And so it will capture the essence of the phase diagram. You'll see a symmetry breaking phase, a symmetry preserving phase, okay, and something in between, which will, we won't be able to find the ground state exactly, the phase transition exactly what it is, but you get qualitatively a correct description already. So product states are very useful, and they are, at least for symmetry breaking phases, and they are very cheap. Okay. But tensor networks are about doing more than just getting this very cheap first picture. Okay? And I ran out of time, so I'll discuss the second example tomorrow.